Wonderful. Well, good morning and a warm welcome to you all. Thank you so much for joining us for the Climate Change Adaptation Program's workshop on improving water use efficiency for dry conditions. My name is Harmony Bjarnason. I work with the Climate Change Adaptation Program. I'm calling in today from the unceded territory of the Silks people, also known as the Okanagan Valley, which is where a lot of this work that you're going to hear about today took place. So I invite you to just take a minute and acknowledge the land from which you are calling in today as well. And I know a lot of you are calling in because you're thinking about your irrigation systems and changes you might be able to make. You know, the spring rains are still going to come and the snow is going to melt, but it looks like it could be very well a dry season, particularly in some parts of the province. So certainly changes we can make early in the season to our irrigation systems are going to be helpful. We get into different drought levels. So that's it for the intro. I will introduce you to your hosts. We have Andrew Bennett and Bruce Naka presenting today, both certified irrigation designers. Andrew Bennett has a Master of Science in Ecology, a couple of decades of getting dirty on farms, and has been designing farm irrigation systems since 2019. He works with several programs that offer education and services to farmers. And Bruce Naka has spent 4 decades in the irrigation industry, designing and installing systems from farms to golf courses, and is actively involved with several water groups, including the Okanagan Basin Water Board. So you'll be hearing from both Andrew and Bruce today. But to start off, I'm going to pass it over to Andrew. Thanks, Andrew.
Thanks very much, Harmony. Welcome, everybody. Looking forward to today's session. It's going to be a real whirlwind of information. And so I'm just going to get right into it. Here we go. So these are some of the topics that we're going to be covering today, a bunch of tools and good ideas. It really is going to come down to a lot of soil, water, and crop knowledge, but also a lot of equipment, things like screens, filters, and pumps, looking at pressures and flows, using simple tools like drill bits to look at your nozzles, catch can tests, that's down here. We'll take a close look at those, how to use your application, get your application rates right. Flow meters on your systems, so a lot of equipment, hydraulic knowledge, and also some bigger picture irrigation ideas. A lot of this will come down in the end to scheduling to make sure that your system is providing your crop the right amount of water for the right time of year. And automation to reduce labor. A lot of what Bruce and I have seen on farms is a lot of extra labor, and trying to eliminate that labor and use your time more productively is also a big part of what we'd like to do. First, a little bit about ourselves. I've been farming for the last 10 or 12 years on my own farm, and before that farmed on other people's farms. My background is in ecology, and I really try and work the two together. Now I live in beautiful Rossland, the unceded territory of the Sinixt and the Naka. So a little bit east of most people on the call today, and of the Okanagan Valley, which is our focus. But these ideas are quite generally applicable in BC, and certainly in the southern interior. Everything we discussed today is going to be very relevant. I work with a number of different programs also that can offer free services to farms is what we really aim for. Bruce, of course, I've been very pleased to work with Bruce for the last few years. He's a real wealth of knowledge, so we're privileged to have him sharing his experience and wisdom with us today. There you go. Lots of, this is just the short form. The long list of board memberships is too long to go into, but really looking forward to hearing what Bruce is going to go into, which is more on the case studies. So what we're going to be doing today is a little bit on the fact sheets that we're coming out with, and a little bit on the case studies where we looked at actual farms and their irrigation systems. Before we get there, though, I want to point out a few resources that Bruce and I have also worked on. We've produced a 12-part video series called The Farm Water Fix. Each of these is about 5 minutes long, and they go through a lot of the same concepts that we're discussing today, but very briefly and in a big picture way so that you can understand where it fits in the system. If you want a deep dive, the Irrigate Better series is a webinar series that Bruce and I put together for 1-hour webinars where we go through a lot of the detailed design information. If you want somebody like myself or Bruce to come to your farm and do an irrigation plan, one of the best ways to do it is to get an environmental farm plan. And with that irrigation design, which you can get funded for free, that irrigation design can then help you get funding for a whole lot of other bits and pieces for your farm. I should back up actually. On this, you're going to see throughout that I'm plugging the relevant Farm Water Fix video. So if you go to YouTube, you'll find these. They're on the Kootenai Boundary Farm Advisors website. They might be floating out there in other places, but if you YouTube Farm Water Fix, this should come up, and Harmony will get you the link also. These are some of the resources that it's all based on. The Irrigation Industry Association of BC, that's the organization that certifies Bruce and myself as designers. A lot of what we're discussing is based on the manuals, the BC manuals produced by the IIABC and the Ministry of Agriculture. And there are other resources such as Farm West and scheduling calculators that are available that are discussed in the videos. And I also draw in a bunch of information from relevant sources in the US, such as Washington State. Okay, let's get to the fact sheets. So we're really excited about these fact sheets. The idea here was to give you a cheat sheet. This is not a textbook. This is not a full treatise. It's a cheat sheet to remind you of the key fundamentals. And we're going to go through a brief overview of these. It's going to go by pretty quickly. Again, the idea here isn't to go away with a complete understanding. It's so that you know where you can go to get this information. A lot of this is going to come back to climate change. And this is the reason that this is so important to us. The climate is changing. Water sources are drying up. And our crops are demanding more water. Globally, this is occurring, and one of the big causes of climate change, the lack of resilience, is problems in the soil and the hydrological systems. What gives me a lot of hope is that the solutions, both whether you're trying to adapt to climate change or help even reduce it, a lot of those solutions are also in proper management of your soil and proper management of your water. And so that's a lot of what we'll look at today. Common problems that we've seen on farms: not enough water. So licensing can be an issue. Unpredictable water sources, poor water quality. All of these can add up to the not enough water problem. Here we've got some poor water quality over here. This often leads to silting up systems, ruining pumps, ruining sprinklers. So getting higher quality screens is something we'll discuss. Poor design overall. A lot of systems are older, and there are new ideas now that can make your design better. Many are badly maintained, and we all know that when our system is badly maintained, but I can't stress enough how crucial it is to fix your system up. All these leaks are common in both sprinkler and drip systems. I have seen drip systems more inefficient than the worst stationary gun system. It is possible to waste water every kind of way. So fix up your system. But more to the point, and what we'll be looking at is not matching your design and your irrigation system to the soil. So this is a drip system, for example, pouring water all over the place. Not scheduling or paying attention to how dry your soil is. Here again, a drip system that suffered in the heat dome. Other cherry farms right next door did not suffer when they were monitoring their soil moisture. And of course, watching the soil, looking for things like erosion and runoff. So these are some really common problems. In brief, what do you do if there's not enough water? Fix your system, monitor your system, consider a new system, and schedule. And get that schedule matched to the soil, the crop, and the weather. Let's get into the fact sheets. There's 5 of them. And the first fact sheet looks at a lot of hydraulics. That's how water moves in pipes. And so we're just going to hit some of the highlights. The 5 foot per second speed limit. If your water goes faster than this, water hammer becomes a problem. We'll have a slide on water hammer in a second. Things that make your water go faster are squishing your pipes. So there's less cross-sectional area. The water has to squeeze through a smaller gap. Having air in your pipes. This is a big problem. Putting in air relief valves. And having pipes that are just too small for the kind of flows you're trying to push around. It increases friction, which we'll look at. But this is a little table here that shows you your absolute volume limits for different sizes of the interior diameter of pipe. Friction and pressure. When water moves through a pipe, it loses pressure due to the friction, and that the friction on the sides of the wall, and that can be increased by the fittings as well. So you need to know what that friction loss is, because we need to make sure there's sufficient pressure in the system to run your irrigation. You're also going to gain pressure going downhill, lose pressure going uphill. All of the fact sheets are going to help you understand how to calculate the amount of friction loss. Also, the type of pipe has a big difference. So if you've got old steel pipe and PVC, even though they're identical inner diameter and the speeds are the same for both of them, the friction loss in PSI per 100 feet is much higher for that old rusty steel pipe. Water hammer. This is really important, as I learned myself the first time I built my own irrigation system and closed a valve too quickly and came back and wondered why there was water flooding my basement. A pressure wave can return very quickly and smash out systems if you do not have, if you have water moving too quickly in a pipe, and if you close valves too quickly, pumps turning on and off, air in pipes, all of these can cause problems. This is a classic one. If your T is undersized, you can get big water hammer here. Make sure your T's are sized to the total flow. Pumps, we've got some information here on how to size your pump based on the amount of total push, the total dynamic head that pump needs to work against. And usually 60% efficiency is a rough guess for many of the pumps that are out there. So you need this kind of horsepower on your pump to get these kind of flows at this kind of total dynamic head. What is total dynamic head? It's the pressure lost to elevation. It's the pressure lost to friction. Plus, it's the pressure you need at the very end to squirt that water out of your sprinkler nozzle or get it out of the drip emitter. Also, at the pumping end, it's very important to have rounded corners on the suction, and your intake screen needs to be sized so that fish are not going to get sucked against the screen. Often we have very large flows coming through very small screens. This is a problem for a lot of reasons, but it's especially a problem because it's illegal. And if fisheries sees a screen that's too small, you'll need to change that. So 1 square foot of 8x8 mesh per 25 GPM. There's the rule of thumb. Okay, sprinklers and guns. The idea here is to get an even sheet of water. And there's a lot of ways you can get it wrong. And the first and most important thing is to make sure the pressure at the nozzle is correct. I really like this tool. It's very simple, fits in your back pocket, literally. I keep it with me everywhere. It's called the pitot tube. You stick a pressure gauge on it and you can stick it into a nozzle and you can see what the pressure is at the nozzle. Here is an irrigation gun running at 18 PSI, which is far too little for an irrigation gun. If you have too little pressure, what happens is it splats out in a ring, it ruins the soil, it smashes the crop, and gives you extremely uneven distribution of water. Too high is also a problem. What happens is it mists on all systems, and you end up with water ending up very close to the riser, and it doesn't actually go as far as it does with medium pressure. Medium pressure gives you the longest throw and the most even distribution. Note, however, that even distribution is not a straight line. Even distribution still has more water in the middle than at the edges. This is why it's important that you have the spacing correct on your sprinklers, at least 85% overlap. That means that your sprinkler throw goes at least 85% of the way to the next sprinkler head. Equivalently, the sprinkler spacing should only be 60% of the diameter of the throw. I personally find it easier to think in terms of 85% overlap. Whatever you want, it works both ways. As you get windier situations, you are going to want more overlap. As the wind pushes things around, you want your sprinklers tighter and tighter together to make sure you don't end up uneven. It's the same thing with drip, and you can use the same tool by I come around, I throw in a punch, stick the pitot tube in, get the pressure, pull it out and throw in a goof plug. and you know what the pressure is right there at the emitter. It's very important because most systems that aren't pressure compensating are going to have a very big difference in the amount of water that comes out depending on the pressure. You can get pressure compensated drip, and it's a very good idea in our mountainous terrain. Those of us who have it going up and down, or if you have very long stretches of rows where you're losing friction the whole way. So application rate, this is a very important number. You need to know how much water is coming out of your system. It's the basis of your schedule. So first you need to know how much water is coming out. You can do this from your spec sheets, and I'm going to show you another way that you can get that as well in a moment. The area is often a point of concern because people wonder if they have to think about the fact that sprinklers are in a circle. Don't worry, you don't need pi r squared or any kind of fancy. You just need to know how much space each sprinkler has to itself. So if you are on a 50 by 50 foot spacing, each sprinkler has 50 times 50 feet of area to itself. Volume divided by area gives you the depth. You are going to get higher flows if your nozzles have worn out. So you use drill bits to see if it's time to change out your nozzle. Catch can tests. So this is where we can really measure your application rate. You could stick your sprinkler head into a bucket and time it. That's one way to get the flow from your sprinkler. This paper boat is just showing how you can float something down a creek and get the cross-sectional area and get the flow of a creek, doing it that way. What we're going to look at closely here, though, are using catch cans. This is important because you can test both the application rate and the evenness. So first looking at drip, we'll talk about both of those concepts in a moment. With drip, what you need to do is take a little cup and walk around your zone. So here's the zone valve, and it's running out on the header, and the water's coming out each of these laterals, and sort of just randomly in a spread out way, testing each emitter for about 2 minutes. So you sit there for 2 minutes, good thing to do with a coffee, collect it in the can. And what I've started doing is using this little weigh scale to measure. I used to carry around a little weighing thing, but it was hard to find somewhere flat to put it. This hanging scale is quite nice. You just hang a cup on it and you can pour it right in the cup and get the measurement very quickly. And you can figure out what the average amount of water you are getting out of an emitter is. Here, 133 mils, which equates to 4 liters per hour, or a 1 GPH emitter. You can do the same thing with sprinklers by spreading them out. Now, the picture here looks different than this diagram. I'll explain both. And the numbers, ignore the numbers for now. You can spread out your catch cans in an even grid between 4 sprinklers, turn on the sprinkler system for an hour or 2, and then collect the water from each can. All right, again, the average of this is going to give you your application rate. You'll need to also know the area of the can because that's your catchment. So to really know the application rate, again, you need the volume, the average volume, divided by the cup's area. Here, though, was a different experiment. We were laying these out in a line so that we could see what the cross-section was of these sprinklers. This farm had been advised to do beds with a single lateral going down the middle of a 50-foot bed using wobblers that can only throw 25 or 30 feet. That means there's only one sprinkler in the middle of a very wide bed. And he was wondering why the crops were doing poorly at the edge. You'll already know the answer. It's because no matter how good your sprinkler is, there's less water at the edge. The problem with this system, there needs to be more spacing. So you can use a closer spacing. You can use catch cans in all kinds of different ways. You can also use it to measure evenness, or technically distribution uniformity. I prefer the term evenness because it reminds us that what we're going for is an even sheet of water, and distribution uniformity is a whole lot of syllables. That said, it's more or less the same thing. What you can do is, in this case, there were 16 cups. You line them all up in order from highest to lowest, and the lowest quarter, in that case, this case, it's 4 out of 16 is a quarter. You get the average of the lowest quarter, and you compare it to the average of the whole bunch of them. So here, 200 mils versus 164 mils. That means the lowest quarter is 82% of 200 mils. So that's more than 80%, which for sprinkler systems is pretty good. If you've got bad nozzles, the spacing is wrong, your evenness is going to drop, your uniformity is going to drop below 80%, and then it might be time to consider tuning up your system. You can do the same thing with a drip system, and you can also do the same kind of thing with wheel moves, traveling guns, and center pivots. We show you how to do each of these systems in the fact sheets. Flow meters. This can be a really, really good thing to add to almost any system. And one of the best ways to use a flow meter in your system, whether it's an analog thing or it's digitally hooked up to your central controller, no matter how it is, you want to measure each of your zone's flows when the system is new. So for example, let's say each of these zones had a 20 GPM flow when it was new. Then down the line, you keep measuring these flows, you notice that one of them is still at 20. Okay, it's good to go. One of them is now flowing a little bit faster. Maybe there's a leak. This 25 GPM, maybe there's a leak in the system. Here, it's flowing a little lower. Maybe there's a clog in the system. That's how you can use a flow meter as a diagnostic tool on a regular basis to see if your system is healthy or not. This farm, this movie here, it's 5 minutes that'll show you the value of a flow meter. Danny is convinced it would have saved him $300,000 had he had a flow meter on his system. It would have caught the leak that for a year was saturating the roots in a large portion of his cherry orchard, and he lost a lot of cherry trees. Soil. A lot of our irrigation is going to come down to understanding the soil, and especially the texture of the soil, the quality of the soil. We want to know things like how fast can it absorb water, how much water can it store, and how much water is there in it now. So we are going to look at some simple ways that you can use your hands to answer these questions. So no need for a lab. Just go out there, dig a hole, and feel it. Before I go further though, I do really want to emphasize the importance long-term to your farm of building up soil life and storage of carbon in your soil. This is extremely important to increase both nutrient holding capacity, water holding capacity, the ability of your soil to infiltrate water, the ability of roots to live happily. If you do these things, your crop is going to thrive, and it's going to improve your resilience to drought, which is what we're really looking at here. So anything you can do to increase soil life. Also, the other thing you want to look at is whether your soil is compacted. You'll want to figure out ways to loosen it. Again, life and carbon is a good way to do that. If your soil is very coarse, it's going to drain very quickly. Again, soil life can help hold more water in a very coarse, sandy, gravelly soil. What you're aiming for is a very complex soil that has lots of surface area. First thing you want to look at is soil texture. And you can do this with a hand feel test. We've got a video on it. And now we have this handy fact sheet that goes along with it that shows you what you're feeling and an order to go through how to feel the soil when it's moist. You make ribbons, you make balls, you see if it cracks, you make little snakes, you basically play in the dirt and figure out where it's sitting on this soil triangle. Texture is the balance of sand, silt, and clay. It's very important because clay and silts are going to hold more water, but they're also going to make it harder for that water to be available to the plant. Sands drain very well, hold less water, but the water that is there is quite available to the plant. So it has a big impact on your water regime. Is it absorbing? This is important because many times we see systems where there's pooling. As soon as there's pooling, it doesn't matter how flat you think your farm is, guaranteed you are suffering from soil erosion. Underneath, you may be having saturated soils that are suffocating roots, and you may also have a problem of leaching nutrients. So you really want to pay attention to what the water is doing in your soil. If it is bare, if it's tilled, if it's compacted, if there's no life in it, if it's dry, all of these things lead to a slower absorption rate. If you do let it dry out, rather than running the irrigation for 8 hours to try and get it wet again, you might want to pulse it. When you pulse irrigation, it absorbs faster. In the first 15 minutes, soil can absorb 2.5 times faster than it can 3 hours later. Again, it depends on the texture, and there's this handy graph here that shows you the ranges of absorption that you can expect from a poor soil to a good soil in these various texture ranges. There is a big range, so you might want to take a look at your soil. It's kind of the most important thing, is to look at your soil. As we say, the proof is in the puddling. All right, so how much can your water store? This is really critical to knowing how to schedule. Look at, you'll want to not be leaching and saturating. You don't want it so dry that your crop is dead. You want this field capacity, and you want to bounce it between this low stress point. Field capacity is the most the soil can store without leaching. You want to get it back up to that spot when you irrigate, and then let the crop drink until it has not yet got stressed, and then irrigate again and bring it up to field capacity. And here is again a chart that gives you an idea of how on different types of soil, the range of total storage in blue, and then in green, the stress-free storage. So this is the amount that the plant actually has access to without getting stressed out. It's only about half of the total storage. And again, rocks, if you have rocks and gravel in your soil, they can't store any water. All of this is explained in the fact sheets in more detail. Soil moisture, you can also tell this with your hand. Dig a hole, feel it with your hand, and use this chart to get an idea of how much soil moisture there is. You can also, of course, use soil moisture sensors, something that we often recommend as a good way to get a more precise understanding of how much water is in your soil at different times of the season, depending on the weather, the crop, and your irrigation. Which brings us to scheduling. This is the fifth and final fact sheet before we move on to Bruce's case, the case studies that we put together. There are 3 different videos on scheduling. I recommend them if you want to get a review on this. I'm going to go through it very quickly now. Unless this is review for you, you're not going to get it this first time around. It can be a little confusing. It all comes down to evapotranspiration. We need to know how much your water the crop has used. That's how much was evaporated from the soil, plus how much was transpired from the leaves. And we subtract any rainfall that was effective. That is the rainfall that actually made it to the roots. That difference is the moisture deficit, and that moisture deficit is the amount we want to irrigate back in the soil. In a nutshell, that's what scheduling is. First place to go is Farm West, to a weather station near you where you can get the reference evapotranspiration. This is how much is evapotranspired, if that's even a verb, should be. It's evapotranspired by what I call a teenage grass. This is a grass that is extremely vigorous, living at home with the parents in a really nice soil with lots of available water, lots of available fertility, and it's growing very vigorously. That is the reference evapotranspiration. Unless that describes your crop, you need to adjust it. We'll also, before I move on to adjusting the crop, though, you can, in Farm West, you can get historical data, and just by going here to click to see daily data and setting the date range for the whole year. And we use this trick a lot in the upcoming slides to look at entire seasons in different areas. Okay, so a crop coefficient. This sounds very fancy. It is not. All it is how much you need to adjust that teenage grass to, for example, give you how much you think your fava bean is using. So on this curve, we're starting here at transplant, say, or first leaf, and going through the season. It could be a week, it could be several weeks, it could be months before you reach full canopy. And then here we've got, some harvest time while it's fresh. And then we're getting later and later in the growth stage of the crop. And down here, if you are harvesting dry fava beans, it would be down here. And the fava beans, I believe, are this brown line. So you multiply your reference evapotranspiration here by 0.25, that's 25%. But up here in peak season, when the crop is using more water than the reference grass, here it's 1.15 for that, 1.1 for that fava bean. That means that it's using 10% more water than the reference grass. And then later in the season, again, it's using less than the reference grass. So you just choose a number based on where you think you are on this curve, based on your experience with the crop, based on your experience with your specific situation. And I've spoken with experts in the wine industry very recently who said that they often go out and monitor their soils and crops very closely for 2 to 3 years until they dial in crop coefficients that are specific to their vineyard. You could do the same thing in any system. Here is an example showing pears in Summerland. I would never know which way to pronounce it. Again, I'm from further east. And what we're looking at here is a crop coefficient multiplied by the reference evapotranspiration through the season, starting here in April and moving through to September. And we're coming up here to full canopy. So this is the crop coefficient. And here is the actual amount of water that was used in millimeters per day. The red dashed line is 2021. So that's our heat dome. And the following year, the previous year in 2019, that same month was quite wet and cool. So it needed a lot less water. This is why it's so important to monitor on a weekly basis, at least, the Farm West evapotranspiration and adjust how long you're irrigating based on what you see. Otherwise, if you irrigated 2021 amounts in 2019, you'd be vastly over irrigating. Or if you did 2019 amounts in 2021, you'd be drying out your crop. Again, looking at hay, same idea. Red is 2021, blue is 2019. Here is the crop coefficient for 3 cuts of hay. And you'll notice when you take a cut, the crop coefficient drops because a cut hay doesn't need as much water. So these are some of the ideas that we explore in these fact sheets. I'm going to run through this really quickly. I want to get to Bruce. I want to have time left for questions. What I'm going to run through is a brief example of how you can actually adjust your automation based on what you see on Farm West. Peak evapotranspiration is what we schedule for. In this case, it's 6.1 millimeters per day for this, whatever place this is. And we multiply that by our peak crop coefficient. So here beets at the top of their curve, they're using 15% more than a grass. Multiplying them together, at most a beet is going to use 7 millimeters per day. We look at our sprinkler system, which is putting out 5 millimeters per hour, but it's only putting it out at 70% efficiency. So actually, to get that 7 millimeters in the soil, we actually need to apply 10 millimeters. To get 10 millimeters in the soil at 5 millimeters per hour, it takes 2 hours of irrigation. Done. Step 1, go to your timer, dial in 2 hours for your schedule for that zone. Now you're set up for peak schedule. But you need to make a weekly adjustment because you're not actually at peak very often through the season. So you go back to Farm West on a weekly basis, you dial in the previous week, you get the daily average, in this case 4 millimeters of water per day for that, what I call the teenage grass. And there was a little tiny bit of precipitation, a little bit of rain. The beets also were not full size. Here they are at about 80% canopy, which is a crop coefficient of about 0.9. 0.9 times the teenage grass evapotranspiration gives you 3.6 millimeters per day. You subtract the effective rain. You guess that your crop has used about 3.5 millimeters of water in that per day in the last week. So you go back to your things, 3.5 millimeters per day is 50% of the peak that you've scheduled for. 3.5 divided by 7 is 50%. Many of these controllers have a seasonal adjust feature. You could just dial in 50% and automatically your zone will now only run for half time, so an hour per zone. You can do the same things more or less with wheel lines, hand lines, guns, or anything that's moving, like when you move a riser around. They're a totally different system. Here we're looking at intervals because of the available soil water. This is where it's really important to know how much water your soil can store. So if you have 3 feet of sandy loam, that can hold 56 millimeters of water. If again, your peak crop evapotranspiration is 7 millimeters per day, if your soil was full of water at 56 mils, then you're going to take 8 days to get down to the stress point of that crop. That means you want to make sure your wheel is coming back, your wheel line or your hand line or your gun is coming back to the same spot on an 8-day rotation so that you're ready for peak. But what happens if your moisture deficit is only 3.5 millimeters of water per day? You need to take time off. You'll finish that 8-day cycle. Don't go right again because there's still water in your soil. You wait a few days. In that time while you're waiting, this is an excellent time to check your soil. Get in there with some soil moisture meters, get in there with a shovel and your hand and just check, because you don't want to wait too long and stress out your crop. Neither do you want to irrigate too soon and potentially leach out all your expensive fertilizer or saturate your roots. And that's it for me. We are now moving right into the case studies. Put up your hand if there is an immediate question, but otherwise I think we could move straight into to Bruce. If anybody has a question though, maybe throw it into the chat. Is there anything in there, Harmony?
Yeah, there was actually one question about who sells pitted tubes or where to find those.
Pitot tubes, that's an interesting one. Bruce, you've made fun of me about pitot tubes. You called them old school at one point, I thought, which is great. I love somebody with a lot of experience calling me old school. I feel that's a fine compliment. You can't find them easily in Canada. I have always had them ordered from the US. So if you find a local source, please let me know. Otherwise, just type in pitot, P-I-T-O-T, in pitot irrigation, because there's also pitot tubes that are used on airplane wings to measure the speed of how fast an airplane's going. You don't want those ones. You want the one that screws onto a regular pressure gauge. Get a liquid filled one. That's going to be a better pressure gauge. And don't pull my kind of rookie error and use a pressure gauge that's going to get maxed out. If you're running a gun at 120 PSI, make sure you've got a 200 PSI pressure gauge on there or you'll wreck your pressure gauge. So there you go, pitot tubes and pressure gauges.
So we'll pass it over to Bruce.
Great. Good morning. Thank you for joining us today. In the course of doing these case studies, it allowed me the opportunity to engage with growers and discuss in-person water management issues that they may be having. Our semi-arid climate, compounded by the drought and heat domes that we are encountering recently, only adds to the amount of water that you will require. 4 distinctly different crops and regions of the Okanagan Valley were visited for these studies that we did. And upon completing these farm interviews, it was apparent that there were 2 common questions that were being asked of me. One, will there be enough water at specific times when an individual crop requires the most water, probably just before harvest in a lot of situations? If there is a shortage of water, what are some of the options of coping with the stressed water supply? But initially, some basic steps towards preparation of water shortages are to have an irrigation plan which accurately depicts your farm and existing crops, and also it should identify any changes that you'll have, any expansions that you'll have into your crop. You want to assess your irrigation system, your existing irrigation system, to evaluate how efficient it is and what would be the most beneficial to improve your system. Okay, so the first farm that we went to visit was the Wildflat Farm. This is located on the Shuswap River in the lovely Mara, BC. The couple that operate this farm have been operating it for over a couple decades. And what we have found is that they have had some issues that we will be discussing. They irrigate and look after in excess of 25 acres. And of that 25 acres, the majority of that is in vegetables. They also have 15 hoop houses which are being irrigated. The this is the breakdown of the property here. If you look at it closely, you'll see on the very top of it is the north end of the property. There's an acre of vegetables that are grown. There's a series of hoop houses that are in the middle there. Our pumping system is just to the right of that in the Shuswap River. Below that, going down the page, you'll see a majority of the farm, which is encumbered by about 13.6 acres, of which half is irrigated at a time. The other half of that is usually left fallow or it's planted in peas or some other cover crop. Below that, you'll see a couple of leased properties, one on the left-hand side of the screen, the little house beside it, and at the very bottom, we have a larger 6-point-something acre, and I don't have my glasses on, which is also leased property. That breaks up the farm. Some of the issues that we're finding, just generally to bring into it, is the labor in moving of aluminum pipes through the system, very cumbersome, awkward. Requires priming, so it's not already what I would call a demand type of a system ready. They have issues with clogging of the filter. There's a filter off of the main line, which again I will discuss a little bit more. And then because you are growing vegetables in market gardens, there's a diversity of crops, so they're at different stages. So you got to be cognizant of when you're irrigating. You're running a row of aluminum pipe, and is it mixed with something else? No, most of the time the aluminum laterals are the same crop. That's fine, but if you're running a couple of zones together, you have to be cognizant of the water needs. Okay, so reviewing a little bit, looking at some of the issues that we're having on this one. Let's start at the intake of the pump system. There's some challenges with your intake of the pipe that goes into the river. Two things, where it is into the river. I mean, ideally, it would be nice to have a cooled off area with calmer water where you could easily service your intake. In this case here, there is a screen. There is a picture depicting a screen, but it isn't the one necessarily that's at Wild Farm. But it is an intake. We are suggesting that maybe the best way to handle this is to put a self-flushing intake screen that utilizes the pressure that is available off of your pump system, diverting some of that water flow very low back in, and it turns a series of nozzles which are continuously flushing that screen as used. It shows on the bottom half of that a river screen, which is on a raft, which makes it a lot easier to run. And if you're in a little bit more fast-moving water, such as a river, as long as you have enough lag on your raft, it is useful. I often see them and that into that separate little pool, it's easier to service. So again, if that's possible, you could do it that way without getting in trouble, impacting your riparian area. You may be able to do that. On the bottom of this slide, you see a filter, and this filter is on the line. We'll discuss it in a little bit more detail, the issues with that filter, which is irrigating exclusively into the hoop houses. Okay, on this one here, we'll talk about the hoop houses. The hoop houses, 15 of them in total. I mentioned just previous about the filter. The filter is irrigating all those, and the reason for that is it has inverted micro sprinklers, meaning that it has smaller orifices on the sprinklers, hence they will plug up quicker. And as a result of the smaller orifice sizes, we need to have a fine enough screen in order to facilitate keeping it clean. In this case here, for the sake of saving time, all 15 of the hoop houses are irrigated at one time. What does that mean? It means that in the process of doing that, our volume of water goes up. The higher the volume of water you are using, the quicker a manual clean screen has to be just clean. And it's a bit of a challenge for these folks because they're having to clean that up times every time it's irrigated. So it's a challenge to irrigate it. What else is used on the farm? The farm is starting to experiment with some more sophisticated high-end sprinklers such as Wobbler, which have a higher uniformity, say, than the old style of impact sprinkler, which have been around forever and a very good starting point. But what's the biggest issue with those? Your nozzles wear out. When your nozzles wear out and are inconsistent in size, it's very, very hard to have uniform irrigation. So changing of the nozzles would be the number one thing. And of course, we're using aluminum pipe in a lot of the system here. Gaskets wear out, you have leaks in the pipe. So again, that's another reason why you don't have even pressure all the way along the system. Presently, on half of the land that is run fallow from crop other than maybe a cover crop, that is all being irrigated by a traveling gun. So traveling guns mean a higher pressure requirement. The higher pressure requirement has to be, you have to remember that, because that higher pressure means that there's going to be maybe less pressure available to irrigate the remainder of our crops. Okay, we have the design of the irrigation system. So what we're talking about is at the beginning of it, as I just went over, we need a self-flushing screen. We're going to put sprinkler heads all through that are on the present hand move system, which is the brunt of the main field there, inclusive of the leased areas. So what we're going to do is, as Andrew was discussing in spacings, we need a spacing to keep it simple, which we'll look at a sprinkler that is going to give you a sprinkler that will have a diameter. And of that, we're going to be covering 60% for overlap. So for example, if the diameter of the sprinkler head was 100 feet, to make it into round numbers, if you want to be 60 feet of that spacing of your diameter, so actually, sorry, it would be, if the sprinkler head had a 45-foot spacing, we'll call it a 90-foot diameter, 60% of that would be 54 feet. In here, we're going to space, because of the setup of it, between the rows, we'll be looking at 60-foot spacing with a spacing between the head of 40 feet on average. So we would have a 60 by 40 spacing. So we would be on an average of 50-foot spacing on the sprinkler heads. What's going to change that? We have to look at wind direction. If you have, and of course, with the river being there and being in a valley, we're going to have a consistent wind direction. So you maybe want to be cognizant of that to modify your spacing, to take advantage, or to put them closer together, depending on your wind direction. Sprinkler heads that we're going to be using in this system are, again, a newer, higher technology type of sprinkler. This one here is called a wind fighter, which is better in windy situations. It is far more uniform with numerous nozzles that are available for it. And later on, we're going to discuss some of these nozzles and how you would modify it on your system. A two-wire system is a system that we're going through a lot right now. It minimizes a whole slew of wires. In this project here, we could be looking at nearly 50 zones. With 50 zones of irrigation, that would mean on a conventional system, where you have wire running out to the field, you would need a common wire joining them all together. But in addition, you need a live wire to each of the zones. So you would need 50 zones. Now, what if you have it make any changes in that system? You may need an extra wire. You wouldn't have it available. So normally when we're doing a conventional system, you run a few extra wires. A good way to resolve that problem is to go to a two-wire system. Two-wire system only utilizes two wires. At each zone or group of zones that are together, you would put a device called a decoder, and that decoder is going to control the zone. So on that two-wire system, you have the flexibility, depending on how many zones it is capable of running as many additional zones as you want up to that maximum. So let's say, for example, your decoder controller was capable of 100 zones. And in this case, if we're only using 50, we have the ability to expand it another 50 zones. Very user-friendly. The schedule that we're going to use on this is we're going to be running multiple zones simultaneous. And that means that the controller has to have the capability of being able to run more than one solenoid at a time. But in doing as such, we can run up to our maximum flow, which is available of 120 gallons per minute. A quick rule of thumb of that, how do we get to a number like that, is if you take the entire acreage that you have, if we were irrigating 20 acres, In the mirror area, would be looking at between 100 and 120 gallons per minute of requirements, between 5 and 6 gallons per minute. Just keeping it very general, so we're not to match a lot of what we're doing. The design is going to utilize, which makes sense, a lot of the existing aluminum pipe. Because of the present setup of it, our spacing is going to vary in the areas where we're using aluminum pipe. But I think if you look at it, the blue lines are the ones that are on polyethylene, which is a 2-inch line. The ones that aren't blue are going to be utilizing the existing hand move aluminum. And again, on that, our spacing will vary. We will be 60 by 30, and that's because the present aluminum pipe has got outlets every 30 feet. Okay, so on here, we're just going to look here at the pressures, and the pressures that are here, if you look at it at the very beginning, on the bottom section there, it shows 60 psi. And then if we walk through that, we're going to see by calculating all our friction losses on our main line or sub main, and all the way down to the end of the line, including pitting loss, we require 47 psi at the end of it. So when you're designing a system, you want to design the system, make sure your pump is capable of that, and we can operate. 47 psi is required to 120 gallons per minute on the farm. Summary of this is, for us, there's far too much time has to be spent on focusing on irrigation in this system. The result of that, we want to improve on that. The pump system requires priming. We want to have a system that the pump is primed, that there's an intake filter so that isn't plugging up on us. And of course, the biggest thing on here is this hand move, very laborious type of a system. We would like to automate that and make it far more efficient for them. If you want to schedule it, there is a weather station, and the closest one is in Gridrod, BC. If we use that weather station and we use an average crop requirement on a crop coefficient, as Andrew described before, we're going to find out that here's the run times. Your peak daily hours of operation is 1.5 hours, and here's the zone breakdowns on the left, and that's how we would schedule. The Lashicks are family growing half cherries, let's say, half apples. They're located on the west side of Lake Country Winfield. They have a total between the two acreages of 20 acres. On that 20 acres, some of the issues that we saw, if you look on the plan that's there, there's a white line down the middle. That's the driveway that dissects the two parcels. We're going to be looking at the parcel on the right, which is just under 10 acres. And here the arrows are going to depict the slope. And so as you can see, there's a really significant slope all the way around, and all leading to cooling down in the bottom areas because of the soils and everything like that. On the left-hand side, there's a very significant water issue there with flooding they've had in a couple of years, and also it impacts growth on the trees. The sprinkler system, the problem we're having with that is erratic spacing in certain areas of both the trees and the sprinklers. One affects the other one, obviously. And we are focusing, as we said, on the right side, the cherries. And on that side there, with the erratic spacing of the sprinkler heads, because the trees are at varying spacing, that's impacted more so on the hilly areas than they are on the flat areas. But with that, it's very hard to get uniform control. There's variable soils from a sandy at the very top of the field, which I'll discuss a little bit in one of the following up slides, to heavier silt and clay at our lower levels that were roots on the bottom. Excess water flows to the bottom. There is leaching. Okay, this is a slide that's going to depict the letter that was sent out to the Lashicks, and it is determining here that on the 10 acres section there, they are saying at the very top, it says your property 2021 agricultural consumption. As you can see, they were just under 30,000 cubic meters on the 10 acres, which is just under 3,000 or just over 3,000 cubic meters. Application of inches of 28.8 inches. And so what that all means is they are suggesting that even though they were underneath their benchmark requirement slightly, that they should be in the 24 to 30 inch range. And lake country, as well as a lot of other purveyed areas from the central to the South Okanagan, or central to North Okanagan, are looking at the lowering of their allocations all to get into that range. And we want to look at what's that going to mean, especially if we have heat domes and other situations, how we're going to be able to look. Some scheduling has to be done on here on this south parcel because of that. Yeah. Next slide. Okay, the south parcel, as I was mentioning about the soils, it's close to 10 acres. Of that 10 acres, 7.8 are in cherries, and there's 1.2 acres of apples in the middle. On that area there, we're looking at, this information comes from the BC Agricultural Water Calculator, which you could ask me a question about that if you're not familiar at the end. Shows a growing season for these crops of 146 days. It shows a peak evapotranspiration of 6.4 millimeters, which is about 0.25 inches per day. A peak flow demand of 64 gallons per minute, and we're averaging out our soils. So we're going to look at the sandy loam, and we're going to say that it requires 1.5 inches. As I mentioned before, we have loam, pine loam on the right-hand side, which is the very top to the middle in the hilly area. And then as we go down, it graduates to sand, quartzose soils, or sand and sandy loam on the bottom. Okay, here's a deeper dive into the soils. So the hilltops, there's lots of gravel, coarse fragments. And then as you get to the hillside, there is an area there which is just straight sand at the top, and it graduates to a coarser sand as we go down a little bit. In the lower areas, you're going anything from a sandy loam at the top 18 inches to graduate away to a silt loam to a clay at the very bottom on the 48 inches. Next slide. The irrigation systems that are utilized on this farm we're utilizing the micro sprinklers, and a lot of it. The next down from the top, so irrigation, there's a little highlight of a micro sprinkler and then an overview, and you can see the micro sprinklers between the trees, and the spacings that vary on those sprinklers will go anywhere from 18 feet down to 12 feet in spacing, obviously impacting your spacing, your application rates. Under tree sprinklers, as in the top of the picture there, the round-head are being used on the apples. I won't go into a lot of discussion about that. There's a few zones of the apples in the middle. Next picture shows the typical of how the zones are set up. And what I do want to point out on that is that there should be an isolation to the manual valve for each group of those two valves. Why? If there's ever an issue and you have a breakdown in one of the valves, that isolation valve will be able to allow you to shut those two zones off and still be able to run through the whole system as is. Also used in the system are micro sprays, which is shown on the right, micro jetted sprays. They're used on the same zone as the micro sprinklers. The issue with that is you have different application rates. Okay, here is the breakdown of the system. Apples in the middle, 1.2 zone, acres of that. Cherries on the bottom, as I talked about, and you can see the zone breakdowns on the entire area. On this here, when we designed the system on the top end, that and one of the slides coming up will show it better, but on near the top west side of the northwest side of the property, we have an issue with extremely sandy soil, and the tree growth in that area is significantly poorer than the norm and the rest of it. We need to address that. When we're going to design a system on that area there, I'm considering use of micro sprays in the entire zone instead of a mixture of micro sprays and micro sprinklers, thus increasing the application rate, which could be a little better on that soil. Higher application rate. I think we should be putting soil sensors in those areas to reevaluate that. And something I haven't pointed out up until now is the Lashets are leasing out this property to a large grower who is running many areas of leased and owned property in that same vicinity as well as everywhere else. What does that mean? It means that he may not have enough time as a grower who is normally on a property. He'll have other employees that will be operating things like that, but they're not going to have time. They're looking after a lot of acreages. It might be a good idea to put in a controller that has the capability of being operated from a phone or a tablet And that way there, you could get that information, maybe look at sensors online and be able to quickly modify his irrigation schedule easier. Crop coefficients, talked about it a couple of times right now, but the crop coefficient, if we look at that line in the middle there, that's the reference ET, carries our crop coefficients, depending on which graph you look at. But Andrew and I like this one here. It's showing about 1.25 is a peak crop coefficient, about 1.3. So that means you're going to have to water 1.3 times longer than whatever your reference CT is. In this case here, it was 0.25 inches or 6.4 millimeters. So that's what our crop coefficient will be. Next slide. So we drop a schedule for all of this. And what I want to point out in light of time is the summary of all this is, if you remember what I recall, presently Lake Country is allowing 30 inches of water per year. They want to change that to 24 inches of water per year, which is a pretty big drop. And what does that mean? It means that if we were to look at it, we were to consider the heat dome, consider climate change. Andrew and I do all our calculations more than one way. What we're finding is, if you look at the three charts that are on the bottom there, the efficiency of the micro sprinkler, we are looking at an average 26 inches of water per year. That's based on the BC Ag calculators, pretty close to that. If we were to look at the very right-hand side, and if we look at 2021, that's our worst year. In fact, with our peak heat in the heat dome and that, we could be looking upwards to utilizing 32 inches of water per year. When I did the calculations based on the sprinkler average sprinklers and doing some improvements, we were around 30 inches per year. So what I'm advocating is that we need closer to what they presently have than dropping it to 24 inches. It could really impact this crop. So we have the Bennett orchard. The issues, Bennett orchard is in Summerland on the top bench, and the west side of Summerland, say the middle, let's say, it's looking down with a gorgeous view of Okanagan Lake. Some of the issues that they're having on there is it's a very old irrigation system that was put in with the planting in the 1980s, early 1980s. It has a system that's only got utilizing 5 zones to water the entire 7.4 acres presently in the planting there. The issues are with only 5 zones, we can't control a lot. Mixture of a variety of trees and that on the same zone. Different emitters being used, so there are some challenges on it. Okay, so here's a photo showing some of the elevation. This is on the very south end of the property. The soil in this area here hits bedrock as early as 12 inches. So that water is just running right down and ended up not where it should be. As you go down the rows, we have a break in the variety of trees that are being in there. So in addition to the soil issue, we have issues with the break of the crop, different crops. So here's a breakdown in the 5 zones that are on the property. So if you were to look at zone 3, for example, we have a mixture of ambrosia, gala, and Spartans all in the same zone. What are you irrigating to? Okay, here's the variety of all the emitters. So we're seeing there's a whole host of different types of emitters. You have some emitters that are pressure compensating, which are going to be more accurate in their flows to turbulent flow emitters in the same zone. As in the very middle of that slide, you see a yellow square thing that's micro spray that's being used on the same zone as an emitter. What does that mean? It means very different application rates. That's not always a good way to go about things. Okay, the soils that were on there, as I said, on the very top of the property, we had some hardpan and bedrock as early as 12 inches. And then you get down to lower depth and we hit some clay and silt. The average on the other areas went from sandy loam to clay and silt. Overwatering of micros on the same zone as the drip was a problem, and there were a lot of leaks and broken emitters, which even more compounded the problem of ununiform application. This is just a quick drawing that we came from the system with some of the changes. A 2-wire system would be nice in here. I was looking at utilizing a very rudimentary form of a weather station on here, which could be used based off of ETs to modify on a daily basis as water is required. More or less, it would ramp up your run times. Flow sensor, as Andrew had described, would be excellent here because of the slope. We're concerned about any breakages and how it would impact the properties around there. So that would also be something that we could look at on this system. Breaking down and improving the amount of zones in the system would make it far more efficient. The grower is presently going to be 50% of, well, maybe not quite 50% was going to be changed to pairs. So we want to make some changes in the system. We want to put some micro sprinklers in the new zones instead of the drip. Why? Because the crops they want, they're concerned about a cover crop for cooling purposes and the likes of that. So anyway, they're all going to be some modifications. The end result is with the system that we're advocating, we're going to need a minimum of 75 pounds of pressure. We're going to utilize a 53.28 gallons per minute, which we have available, and it's going to take 20.48 hours per day to irrigate. This is very crucial when you put your irrigation schedule in it, all that in there. At the end of the day, if you want to irrigate every day, you got to make sure it's under 24 hours. Okay, we went to the Thomas Ranch in OK Falls. This is a 200-acre irrigated farm on the top east side of OK Falls. It's got a whole series of different irrigation systems that are going anything from very high-end pivots down to hand move systems in certain areas. They have water sources in this place here. Some of the issues they're having, the two water sources are McLean Creek and Thomas Creek. The McLean Creek, we're having issues with that one right now with some turbidity in this, and the sprinkler reels that are being used, they're having problems with their turbines plugging on them. So they can't use their traveling guns without a lot of maintenance. The wheel moves, as described before, there's the radicacy and the different nozzles that are being used. Highly recommend changing those nozzles to improve on that. I did want to mention that the Thomas Creek end of this property, the infrastructure is all there. It's all connected. It was very helpful in 2021, I believe it was, when there was a fire right at the very east end of the property that was caught early because of the fact that they had that water access to get at that area there. I also wanted to point out the reservoir is an existing older reservoir, and work done to it would allow us to utilize the rest of our water license. Next slide. Okay, so soils that were on this property when we were out there. On the right there, you see a soil survey. That's an existing soil survey, the Winslow survey. And what we found is it's showing sandy loam down to loamy sand at the bottom. And in that area there, when we actually dug down and checked it out, we found that there was a lot more loam, much less rock than it showed on the survey. What does that mean? If you calculate it out based on your soil types over the 4-foot root zone on, say, an alfalfa crop or something like that, we're going to find that we have a little bit more storage than we thought. And with a 0.26 into ET in that area there, we could have up to an 11-day cycle. If we were to look at it the other way, that number would be different. Next slide, please. Okay, I had mentioned there's a turbid issue with the McLean Creek source, which was plugging up the turbines on the traveling guns. One suggestion is to put on a self-flushing screen onto that system there, which has to be fine enough, obviously, to take out that fine silt and sand system. You can get them. They have an orifice plate. The orifice plate has a series of holes in it. And you can get the spin plate that goes in there with a sand guard because of the sandy conditions. The one that we had advocated, because the line is 12-inch, was around a 12, the largest of the filters, which is a 12-inch one. The issue with that is if we reduce the flow going through that side versus the Thomas Creek side, we may have to downsize that to a 10-inch filter so that we get enough velocity to clean the screens properly. On that inset, you see the filter in the drawing there, and in there you see two different styles of what are called air relief valves. Air relief valves are failing on a lot of irrigation systems, majority of irrigation systems. I want to point out that air relief valves are crucial on anything that you have a filter or pressure reducing valve. Any high point, or on average, every 1,000 feet in your main line is good to have an air relief valve. Why? Air relief valves help a system to operate far more efficiently. Air trapped in a line can cause you anything from vacuum problems, tucking your pipe flat, to enhancing the ability for water hammering and surging, which can break a lot of pipes on you. Air relief valves, appropriately spaced, can resolve a lot of the problems that a lot of people have had over the years. Okay, some of the other changes we're looking at, it is already in the works. There are pivots presently on the system. The challenge with them is there isn't a power source at those locations. So they've had to use a generator to create the power, which had to be moved around. That's being resolved right now. The two existing systems, along with a new one, or a new pivot that's going to go in on the east side of the property, will allow more efficient irrigation. It's going to, presently, the area that's shown on this slide is being irrigated by a wheel move. The wheel move can then be moved to another section so that we have more devices to irrigate the area and become more efficient in how we go about it. And those wheel moves, as emphasized before, should be changed because there is some inefficiencies in the sprinklers with worn out nozzles and old brass impact. We want to go to the higher uniform type of gray plastic one, as such as shown in the picture. Right beside that, you see a pressure gauge, and that is Andrew's old school pressure gauge, which isn't liquid filled, and they break down a lot easier. Put a liquid filled pressure gauge in. The brass device underneath it is a pitot tube. Where can you get pitot tubes, by the way? Any of the agricultural specialized irrigation stores, if they don't have it in stock, it's easy for them to order it from their suppliers. And when I was in that business, we were bringing in pitot tubes from some of our, like, for example, Nelson Irrigation would have pitot tubes. Okay, this is just showing the infrastructure and how we would go about making the modifications to fully integrate the Thomas Creek main line in with the existing main line coming from McLean Creek. So we're going to go from Thomas Creek, Y0 at the top end of that. And if we were looking at exclusively the storage aspect of this, we could follow that line all the way down to where you see on the left-hand side of your screen, Fed 0. There's an elevation drop over that area of 295 feet. So we're going to create just around 120 pounds of pressure to do that. So we have lots of pressure to do that. If we reverse the flow and we were to feed from the reservoir down to connect into the irrigation main, as it's shown there, we don't have enough elevation. We'll probably need a booster pump in order to facilitate using that for irrigation purposes. That's how you would connect the main up, and you would have a nice even flow, maximizing our water license the way we need it. And the other thing I wanted to point out is we could do something for the community here. We're in a wildfire transitionary area, and having that capability with big water like that to put out any fires in the immediate area for the community would be something that would be much appreciated by all. In closing on this, the reservoir that's presently there, it's dug fairly, most of it. The area that's up there is between 15 and 20, about 15 acres off the top of my head. What Andrew had shown on the slides on that is there were two options. Under low water, we had the ability to, I believe it was store the neighborhood of over an area of 1.4 acres. So this is a very shallow end of it. We would have the capability of storing 10 acre feet, not a lot of water. If we were to expand this, and I emphasize this, there could probably be some engineering requirements for dam control on this if it was excavated out. But I mean, the maximum that was available there is we could have an area of up to over 11 acres, surface acres of area. And depths that we went down to at its maximum, we could be storing up to 130 acre feet of water. What does that mean? If you had 100 acre feet of water, 130 acre feet of water, that would give you the capability of having 3 feet in depth of water over 43 acres. So you'd have enough to irrigate up to 43 acres with that extra reservoir. So in closing on the Thomas Ranch, maximize they have to maximize their efficiency. and improve on the existing system and the infrastructure. The filter would be important on both sources, Thomas Creek and the McLean Creek, in order to make sure that the systems are operating properly. The pivots will definitely help out in that instance, and the reservoirs will definitely help for issues when we have a drought or heat dome situations. That's all I have for you folks. Thank you very much. I don't know where we sit. If we have the capabilities of answering questions, we'd love to help you on that. I leave that, Harmony, in yours and Andrew's hands. Thank you.
Yeah, well, we just should definitely thank our funders. Maybe Harmony, or is this slide good?
Yeah, I can do that, absolutely. So this project is part of the climate change, the climate change adaptation program. We have funding from multiple partners from within the Okanagan. So thank you to the Regional District Okanagan Similkameen, the Regional District of North Okanagan, and also the Okanagan Basin Water Board. And then additionally, funding has been provided for this project through the Canadian Agricultural Partnership. The program itself is administered by the Investment Agriculture Foundation of BC. So thank you to all of those partners who made not only this project possible, but also this webinar. And with that, I will stop the recording. We will move to questions. Thank you so much, Bruce and Andrew, for your presentations. I know there's a couple in the chat, so we can get straight into that.